Okay, so now let's take a look at some voltage regulation mechanisms. And the first one I want to discuss before I get into the line voltage regulator is how we can actually do this with the substation transformer winding. And what you'll sometimes see is that the substation transformers on the primary side would have a set of tap positions, as kind of shown here, where we could actually uh, change the physical connection to. And so I don't want to get into all the details of this. I mean, basically, we have to make sure that we're not breaking current. And so you have to have a mechanism where you kind of move the contacts around in such a way where you don't break the current. But basically, if I can change the tap position, effectively what I'm doing is I'm changing the turns ratio. I'm changing the number of effective primary windings. And by doing that, I could regulate the voltage on the low side. So typically this would be done on the high voltage side because that would correspond to the lower of the two currents on the transformer. And this particular mechanism would be what's sometimes referred to as a tap changing under load, or TC well. Sometimes this is called an LTC, low tap change. Sometimes this is referred to as an OLTC, on load tap changer. But these all refer kind of to the same thing. Now, sometimes what you see in distribution substations with a transformer is you might have tap positions, but they're not adjustable without de-energizing the transformer and changing those connections. And so, for example, what you could see is you could see something where you'd have like a minus 2.5%, a minus 5%, plus 2.5%. No, this is kind of sloppy here, and a plus 5%. And the reason you would do this is, maybe to account for deviations in transmission voltage, or trying to get the voltage up higher at the top of the feeder. You might want to be playing around with these tap positions, which could be fixed as well, right? That would kind of bias the operation of the transformer. So anyway, this would be one way you can do this. But my experience, at least in looking at the distribution circuits in this area, what you would typically be doing that with voltage control on the secondary side of the transformer, in terms of using these auto transformer arrangements we refer to as line voltage regulators. So let's get into this topic then, line voltage regulators. These are also called auto transformers. That's actually the type of connection they are for the transformer. We'll see in a little bit what that involves. But basically what you can do with these line voltage regulators is you can set these up where you can get small increases, and by small I mean plus minus 10% changes in voltage along the feeder. And as far as the range, usually plus or minus 10% is the standard. These could also be set up for like plus or minus 5%. A lot of cases, these windings that are used in the auto transformer relationships are going to have maybe like 16 taps. And given that you can flip around the winding, basically reverse the polarity of the connection, basically what this is going to give you is 33 position options, as we'll see in just a little bit. So if you have the ability of doing plus or minus 10% with 16 fixed taps, and if you can basically flip the winding around, what this is going to give you is, over the entire range, if you have like the 20%, you're going to divide this through by 32. Then basically this is where you get the 5/8% change, which corresponds to 0.75 volts on 120 volt base. And so what this does is this gives you the resolution of the change. In other words, if I'm going to make a tap change, it's got to be in increments typically of 5/8%. And so I can't continuously regulate the voltage, but I can regulate voltage within these interchirp positions. One other thing to keep in mind is with these auto transformer arrangements is that the primary and the secondary winding are to be connected together. And so if we're talking about the amount of rating required, it's not going to be the same as having a regular transformer where we need to have isolation between the primary and the secondary side. And you'll see a little bit that if I have like a certain current rating, say like a 200 amps, and if I'm operating nominally around 13.2 kV, that the size of the transformer turns out I'm going to need for this, if we have a 10% boost, is only going to be 264 kVA. And so you don't need a really huge transformer for doing this. So the way these autotransformers would be built, again, is by using what's called an Autotransformer connection. And if you have two windings on a regular transformer, let's suppose you have like the high voltage side and the low voltage side, the way you do this is you take the second winding, you take the secondary winding, and you stack it right on top of the primary winding, and you make a physical connection right here. What this means is you'll have some current coming in from the source side. Some of this current's going to go off in this direction, and then you're going to have also some current right here, I2. But what this means is that you're not going to have this galvanic isolation anymore. You're actually going to have a direct physical connection between the two sets of windings. This primary winding is a lot of times referred to as the exciting winding or excitation winding. And then the winding on the secondary side is what's referred to as a series winding. Because if I have a voltage V1, then basically what the load voltage is going to be V1 plus V2, or you can think about that as a boost, which is going to enable V load to be actually higher than V source. And I could also flip this winding around to get a voltage drop instead of a voltage boost in this case. So note in this case, there's no magnetic isolation like you would have like in a regular transformer connection. Now, to show you what effect this has on ratings, let's take a look at an example where I have a transformer that's rated 7,200 volts on the high side, 720 volts on the low side, and it's 100 kVA, right? So let's take a look at what would be the power handling capability of this device if it were going to be connected up in an autotransformer relationship. So what you're going to have is you have the primary winding. It's rated for 7,200 volts. If you take the 100 kVA divided by 7,200, then we would see we could carry 13.9 amps in that primary winding. Now I make a physical connection here. Then on the secondary side, what I'm going to have for a current rating is going to be that 100 kVA divided by 720. That's going to be 138.9 amps. And the total amount of current we could have on the source side then would be the 138.9 plus a 13.9. So what's the power handling capability? Well, if I'm boosting this up by 10%, on the load side, I'll have 7,920 volts. Multiply this by 138.9 amps, and this gives me a power handling capability of 1,100 kVA. So it doesn't require a really large transformer to get a voltage boost. Basically, I just need to have, like for a 10% boost, I just need to have 10% of that kVA rating available. But basically, this kind of shows kind of like, I guess you can call it the magic of using an auto transformer, is I don't really need to have a large transformer to get a voltage boost. So how do I get the adjustable voltage? Because in this case right here, this voltage increase is kind of fixed at 10%, right? And I want to be able to change this as a function of time, or depending on what's going on in my circuit. Well, the way we would do this is I would take this secondary winding and I'd put taps along it where I could use up the entire winding, or I can just use up none of the winding, basically. And so this would be kind of like tap position 0. It's just basically making a hard connection to the source, or I can use more or less of the winding. If I was using 16 taps worth, I'd be using the entire winding. If I'm using like 8 taps worth, I'm using half the winding, right? And so what this means is if I neglect the voltage drop across the windings, then the load voltage is going to be the source voltage, which in this case is 7,200 volts, plus the tap position divided by the total number of taps times 720. All right, so I can see what happens with tap equal to 8 or tap equal to 16 or tap equal to 1, etc. So basically, by adjusting this mechanical position, what I can do is I can get an adjustable voltage. And what I could also do is I could flip this winding around. Instead of getting a voltage boost, I can get what we call a voltage buck, which means I'm dropping the voltage instead. Okay, so this is the way we would do line voltage regulation in a lot of different cases. This actually shows what a voltage regulator looks like, and I know you can't see this in detail, but the thing I just want to point out is that you would typically have a meter at the top, which would show the mechanical tap position. This would go between plus and minus 16 in a lot of cases. And the older types of devices, the controls are located right on the side. That's actually kind of mounted into the unit. Nowadays, we might actually see a separate controller, but in the older units, the controls are actually integrated in. And what takes up a lot of space in this case is the mechanism for actually doing the tap changing. The transformer itself is pretty small, but then to have the tap changing capability is what takes up a lot of the space. And so this shows a single phase type of device. We could have this be three phase. This shows a Siemens device that could be located in the substation, for example. So if you had your transformer and you were regulating like all the feeders coming out, then you might have this device in here, and then you would have your bus that all the feeders are connected to. So this is something you see a lot in this area, is that you see this three-phase voltage regulator. We would typically keep the tap position in each of the three phases the same in this case. And then you can also build this out of a three-phase unit out of individual single-phase devices. And so you'll see this sometimes mounted up on poles. It's kind of, you can't see the third device, but they're kind of mounted up around the pole like this, where you have the phase A, B, and C. You can also see this mounted up a lot of times on platforms. And so this would probably be in the NC State area, probably a more common sort of thing to put things all up on a platform like this. And again, you have this little meter on here, which shows you the mechanical position, and it goes all the way up to plus 16. Or if you flip the series winding around, it can go all the way down to minus 16. This shows another schematic of how this would actually look. And again, what you're going to have is you're going to have the exciting winding. And basically, it's this series winding that would have the taps on it. And so this is only showing 8 taps in this case, but you actually have like 16 tap positions. And then what this mechanism would do is it would move back and forth in order to adjust the tap position. And so anyway, this kind of shows a series winding and the fact that you have the switch that could flip the series winding, so you can go back and forth between a boost and a buck in this case. And note in this case with these regulators, instead of talking about a primary side and a secondary side, we typically talk about the source side and we talk about the load side, where this SL connection would be common between the two sides, and there's actually a physical connection then between the two windings. This shows a nameplate for a device, for an Eaton Cooper power system device. And what you'll typically see is you'll see these devices would typically have certain rating sizes associated with them. And so you can see this is set up for 13.2 kV line type of a service, where per phase it'd be 7.62 kV, and it shows a lot of the detail in terms of the taps and stuff that you would have available. And you can see in this case that this is adjustable in these 5/8% of a step in this case. typical regulator ratings are shown in this table. And you can see for the smaller sizes that the output current rating kind of matches up with the rating that we have for the CT in the control circuit. We'll talk a little bit about how the CT is going to get used. So the control circuit actually is monitoring the current, and you would have to step the current level down for use in the control circuit. And so usually it's for the smaller values for these regulator sizes, the current rating of the regulator matches up with the CT size. When you get into some of these larger units, there's not a 1-1 correspondence anymore necessarily between the regulator current rating and the CT primary. But for the circuits we're going to be using in our project, or the regulators are going to use in our project, we're typically going to be using a lot of these smaller current values. And one thing I want to point out, when you're doing maintenance, one thing you have to watch out for is you need to make sure that if you do maintenance on one of these devices, that the tap position is going to be in the 0 set point. So why would you want something like this? Well, let's suppose that I'm doing maintenance on this device. If I do maintenance, what do I do? Well, when I do maintenance, what I'm going to do is I'm going to short this device out right here. I'm going to close the switch and basically take this device out of service. Now, what happens if this tap position is not at 0? Well, if this tap position is not at 0, if it's like tap position 3, you're going to have voltage across the series winding. And when you try to isolate this out of the circuit and you're shorting out the S to L position, you'll have a voltage that you'll be shorting out. You're going to cause a huge fault current. So the purpose of this slide here is to make sure when you're doing maintenance and you're bypassing this device, to make sure this is set to the tap equals 0 position. Now, as far as the controls on this, there's a lot of different types of controls. Obviously, there's what we call the band center, and this is really the voltage set point if you want to think about that way. We call this the band center. And then when we're operating this device, we're going to specify a bandwidth that this voltage is going to stay within. And we talked about this bandwidth before. Something else we'll have before we activate the control, if we're out of the voltage range, we'll have a certain time delay in there that we could set. And then something else we have is the ability of accounting for voltage drop on the line between the regulator and the load. And that's something called LDC, or line drop compensation. We'll get into a little bit. You have some other advanced settings in here called like first house protection, where we want to have an absolute high value limit on the output. And then we have these operational modes called bidirectional cogeneration, which we'll get into just a little bit. Now, I'm showing in this case an old analog controller. And this has the little dials on here and everything, where you can see everything that's going on. I know this is kind of an old controller, but this, to me at least, actually helps me explain a little bit more what are the options on the controller. Because if I look at one of the new digital controllers, say like a newer Beckwith digital controller, like an M6200A, well, this has an LCD display on it, and I could navigate through here and I could punch in the values, but it's kind of hard for me to kind of keep referring to the control options, right? And so just realize that these controllers are actually going to be looking something like this, but from the standpoint of explaining the different controls, it's a little bit easier for me to talk in terms of the older analog controller. So anyway, what are the controls you could set? The first control you would be looking at would be what we call the band center. In this case, it's called voltage center of band. So this is kind of like the target value, if you want to think about it that way. And you can see that this is set up on a 120 volt base. So the idea would be, if I want to have like a 5% voltage above nominal, then I set this band center to 126. A lot of utilities might use values like 125 or 124. The other sort of setting you can have on here is the bandwidth. So keeping in mind that you're going to have like a 5/8% usually a resolution in voltage, what you would do is you would set the range over what you let this voltage drift before you would cause a tap change. And when I say 2 volts, basically this would mean 1 volt over the band center, 1 volt under it. And so if my setting was like for 124, and if I had a bandwidth of 2 volts, then basically what I would be looking at is if the voltage goes above 125 or it goes below 123, then I'm going to adjust the tap to get that voltage back within that bandwidth. So 2 volts would be a common setting. You can't do any better than 1.25 because of the resolution you have on the taps. But 2 volts would be a very common setting. And then if you have a lot of intermittent load, you let that go out to maybe like 2.5 or 3 volts. So again, if you go back to what this voltage profile is going to look like coming out of a voltage regulator, you could have this band center set up to maybe like 126 if you wanted to. You have to realize that it would actually be anywhere between this upper and this lower part of the bandwidth. And what this means is there's always going to be a little bit of uncertainty as far as what that voltage is actually going to be at a point in the feeder. Usually for our calculations, when we do the calculations by hand, we usually assume the bandwidth's just 0. So we're just kind of doing our calculations on this dashed line, but just realize in practice, there's always a little bit of uncertainty about where the voltage is going to be at due to the fact that we have these regulators with these discrete tap options. Another setting we have is a delay. We have a time delay. And there's actually 2 reasons that we would set this here. Normally, if we have adjustable load changing constantly, we don't want to track that load too much. Otherwise, the taps are going to change too often. So what we would do is we would put a delay on here where if the voltage goes out of range, we make sure it stays out of range for a certain time delay before we adjust the tap again. So that just reduces time wear and tear on the regulator. What we'll also do too is we'll also want to have coordination between our regulators. And so we might have a situation where I have like a regulator at the substation, we have a regulator downstream, and then maybe I have some load change on the circuit. Now let's suppose the voltage goes out of range. What regulator do I want to have first? Well, normally what you do to coordinate it so you don't have these 2 devices fighting each other is you usually want to have this device given the opportunity to change first. So it would have a lower time delay than the downstream device. And maybe what you would do is you would make sure these are coordinated in such a way where maybe there's going to be a 15 or 30-second difference in the time delay, just so you don't have these devices acting at the same time. All right, so we normally set this up where the upstream device has the smaller of the 2 time delays. And we could have situations where we maybe have like 3 or 4 line regulators in series. And so what you would do is as you go down the feeder, then you would just simply keep adding to the time delay difference to make sure that the upstream device would be given an opportunity to work first. The other thing that we have for capability on these voltage line regulators is what's called a line drop compensation. So let's suppose that I have a line regulator and it's adjusting the voltage. And then I have line impedance. And really what I'm interested in doing, what I'm really worried about is trying to set the voltage here, right? So the problem is that if I have some resistance and reactance, and if I've got a load current, if I really want to set this value at the load, what does this control value for the regulator need to be? Well, what we need to do is we need to set this up where what I'm trying to control here is going to be V set plus this voltage drop VD. In other words, I have to boost the voltage up just a little bit more to take into account the line drop that's between that regulator and the load, right? So the way we do that is through what's called line drop compensation. In a way, what we're doing is we're giving the regulator some indication of what this line impedance is through setting these R and X line drop compensation values, right? So what this means is if we're going to do something like this, is that the regulator control needs a circuit, and this in the old days was an analog circuit. Nowadays, this is obviously all digital, but it needs a circuit equivalent where what it has is it has a model of the line resistance and the reactance. It knows the current on the load side of the regulator. It knows the voltage on the load side of the regulator. And basically, given that you have a regulation set point that you want at the load, what this little control circuit does is emulates what this voltage drop is. So if you put in the right value of R and X, it measures the current, and it has the voltage information. What it's going to do, it's going to figure out, well, how much additional voltage boost do I need to have, where this is really my voltage set point. How much voltage do I need to add on here to take into account the drop across this line? Okay, so the actual regulator output in this case is not going to be V set. It's going to be V set plus whatever that controller thinks is the drop across the outgoing line. What we're going to do in class is we're going to model this using K factors. Basically assume kind of a constant current load and use that to approximate what's going on. Now, what is a little confusing about line drop compensation is, as far as the settings, you would think that you could plug in an R and X directly, right? That would actually make a lot of sense. But the way the older analog controls were set up is they were set up in terms of analog circuits. And so what you would do is you would take the actual current that you're monitoring and you'd factor in the CT ratio that you're stepping it down to for your analog circuit. And then you would also factor in what is the ratio between the primary nominal voltage and 120 volts, because that little analog control circuit was set up to operate at 120 volts. And so it was kind of set up for 120 volts where at the CT rated current, you'd have 1 amp in there basically. So what you really have for R set and X set is a set of values that are actually having units of voltage, where what R set's going to be is going to be the CT ratio times RL divided by the PT ratio. And a similar value here for X set. And that's the thing that confounds a lot of people sometimes about using regulators. Why can't you just put in R and X directly? But because of the history, you've actually got to do an R set and an X set. And they're just simply related by these two formulas here, okay? So again, if you're converting 7,200 volts into 120 for the control circuit, this N value PT is going to be 60. And then if you've got a regulator that's got 100 ampere output, usually that's going to be the same as a CT ratio. And that's just what goes into the formulas in this case. So as far as the impact of line drop compensation, again, let's suppose I had a circuit and I've got a station regulator and I got a downstream regulator. What we're trying to do is we're trying to make sure that we can keep the voltage high enough for the load at the very end of the circuit, right? If we don't have line drop compensation for the circuit at all, what we're going to see is we're going to see the regulator just simply going to control the voltage, say like at 126, let's say, regardless of what the load current is. So if we had a really heavy load on the circuit, this is the profile you're going to see for heavy load. The voltage drops really low and then goes back up high where we have the voltage regulator, the line voltage regulator near the load. However, if the current was lower, then we're still starting at 126. The voltage doesn't drop as much, and then it jumps back up at the regulator. Now, what could you say about this particular circuit here? If we don't have line drop compensation, well, if I want to make sure that I keep the voltage boosted up under the heavy load conditions, what's going to happen is under the light load conditions, I'm going to be running high. I'm going to be running high around 126 volts. And the reason this might cause some problems is it turns out there's a relationship between load consumption and voltage, where if voltage is high, that tends to boost up kW demand a little bit. There's a constant impedance characteristic for the load. And so if we're running high voltage all the time, we're kind of forcing our consumers maybe to consume a little bit more kWh. So this is kind of undesirable. We don't really want to see this voltage varying all over the place like this at these points 1 and 2. We'd kind of like to, keep that voltage deviation a little bit smaller. And if I don't do line drop compensation, this is going to be an issue. So if I do line drop compensation, basically under the heavy loading conditions, I could still start at 126 and the voltage would drop down and I would boost it back up again. However, if I had line drop compensation, what I can do is I could actually get by with a lower voltage. If I know I don't need to have as much boost under light loading conditions, I don't boost up that voltage as much this time. And what this means under light loading conditions, I have a little bit flatter profile. And so you're going to see this later on when we work some of our examples. The advantage of the line drop compensation is kind of twofold. It makes sure that we can keep our customer, like a critical customer, regulated. But the other thing is it also kind of helps us kind of levelize our voltages a little bit. Another thing I wanted to mention, a couple of things I wanted to mention is we do have what's called first house protection. So say if I had this voltage regulator here, and let's suppose I had a residential customer that was really close to it, I want to make sure that I don't boost this voltage too high where I might have the voltage go up too high for this customer and maybe start burning out load like light bulbs. And so what a first house high does is it makes sure that this voltage coming out of here doesn't get above a certain fixed limit. So that's what's called first house high. The other thing you'll see on here too is they have what's called bidirectional mode or cogeneration mode. And the reason we would have something like that, let me go ahead and erase this again. The reason we'd have something like that is, let's suppose that this recloser was open because we had a fault up here. And so we're going to open up this circuit breaker. We're going to open up this recloser. And then to supply load, we can backfeed it by closing this tie switch. So what this means is we would actually have load being fed from an alternate backfeed, and it would be going through the voltage line regulator, but in the opposite direction. Why would we need to have a different mode? Well, now instead of regulating the voltage on this side, now what we want to do is we want to regulate the voltage on this side. We want to regulate the voltage always on the load side of the circuit if we don't have any other sources in the system. So that's what bidirectional mode does, is it senses the direction of power flow and changes what side of the regulator we're regulating the voltage for. Now there could be a situation where instead of having this scenario where I have an outage, I could also have a scenario. Let me get rid of this right here. I could also have a scenario in the circuit where I had distributed generation. Let's suppose I had distributed generation like right here. I have DG. And what this DG could do is it could push power upstream. Now the regulator is going to see a change in power flow, but we do not want the regulator to swap mode. We still want the regulator to regulate this voltage on the load side, even though the DG is pushing power back in the opposite direction. So that would be where we'd use like cogeneration settings on the devices. So normally these regulators will have different modes, and we could actually switch back and forth depending on the scenario. All right. So one last thing before I get into the example is, again, if we take the spreadsheet, I could also use the K-factor analysis to predict what's going to happen if I were going to play with the settings. And so in this particular case, what I'm trying to do is I'm trying to levelize out this voltage for certain loading conditions. And I could start out really high. I could have this be 126 at the station. And then when I get to this line regulator, I could boost it back up again in this case. But then what you would see is you would see a lot more deviation and potential deviation like in the voltage ride. And again, as I mentioned before, we may not want to ride right at the top of the range because this could cause some other operational issues. And so what we would do instead, again, we would probably choose a voltage here that's maybe a little bit lower, maybe a 124. The voltage drops. Maybe we don't need the regulator here. Maybe it could be a little further downstream. But then what we'll do is then once we get to the point where we have the regulator, we'll boost this up to 125. And as I go back down toward the load again, you can see this drop off. We want to make sure that this is going to stay higher than some sort of set point, maybe like 118 or 119, something like that. So I'm always looking at this voltage at the end of the circuit and making sure that that's not going to drop too far. And so what I can do through the set points and through the placement of the regulators, I can actually kind of design a voltage drop curve. I can do some engineering around this. And then if I thought I needed another regulator, that would give me another boost further down line. I could probably levelize it even further, but these regulators are kind of expensive. So I can only do that to a certain extent. But I can actually shape the voltage curve through the selection of these set points into the location of these regulation devices. And what I'm doing in the K-factor analysis for this particular problem is I'm calculating what these voltage drops are on the different sections. And then when I get to a regulator, then basically what I can do is I can model the boost that I would have as a function of the tap position. Okay, so let's go ahead and we'll stop this video segment here, and then I'll go through an example that kind of shows some of the design considerations in setting up a line voltage regulator.